This instrument provides automated leakage testing based on the SMACNA HVAC air duct leakage test manual. The DALT 6900's HD touchscreen display guides users through a step-by-step process, allowing you to select from multiple configuration options. Quickly toggle between temperature units like Fahrenheit and Celsius, and airflow units like cubic meters per second, cubic feet per minute, liters per second, or cubic meters per hour. The DALT 6900 does not require the use of orifice plates, decreasing the time required to conduct tests as well as the room for error. Perform both positive and negative pressure tests with a simple rearrangement of the hose, saving you even more time when dealing with varying test requirements. All of the parts that are needed are already included with the unit, removing the need to order different components for different projects.
Good afternoon, everyone. I'm Sim with AABC, and I'd like to welcome you to today's TAB Talk webinar, Building Decarbonization, Key Test and Balance Issues and Solutions for Occupancy, Wellness, and Sustainability. I would also like to go ahead and thank our sponsor, ScannerMax, for supporting this session. Just a few housekeeping items before we get started. Our presenters will be holding questions until the end of the presentation, but we encourage you to submit them at any time using the Q&A button. If you happen to be experiencing technical problems during the webinar, please use the chat function to inform the panelists so that our producer, Will, can assist you. This presentation is being recorded and will be available for viewing in 1 week. In terms of continuing education credit, everyone in attendance for the full webinar will receive a certificate of attendance sent to their email within 24 hours. And finally, if you are a certified TBE or TBT, your CEUs for attending this webinar will be automatically uploaded to your respective portals after the webinar. Let's go ahead and welcome today's speakers. First up, we have LaPera. Al has 47 years of experience in the HVAC industry, working on a wide range of building types, including educational, healthcare, and commercial facilities. His expertise spans HVAC system design, commissioning, energy analysis, and construction oversight from project start to finish. Next, we have Robert Kolnes. Robert brings over 40 years of experience in test and balance with a career that began in 1983. Known for his precision and leadership, Robert played a key role in projects like Allegiant Stadium and continues to mentor the next generation of technicians while setting high standards in system performance and integrity. And without any further ado, I'd like to hand it off to our speakers to kick us off.
All right, very good. Good afternoon, everybody. I'm Al LaPera. I've been doing this for a long time. I think Sim was trying to tell Robert and I that we're old, since I have 47 years experience. He's got over 40. We're part of the greatest generation together, if we look at it that way, right? But anyway, I think I'm really excited to present with Robert today, because he brings a good counterpart to me on this. So without further ado, I think we should get started here. Here we go. So today, obviously, we're talking about building decarbonization, key tests, and balance issues and solutions on how to do it. So I want to start out first by making sure everybody completely understands. You got to think about this when you were a kid, right? You couldn't eat your dessert until you ate your meal. Whether you wanted to eat your meal first, mom and dad would not let you go any further. So the first beginning portion of this is going to be where you're going to have to eat your spinach, right? I'm going to tell you things that you may know or may not know, but you have to get through this and understand why we are what we're doing to get all the meat and potatoes later on. I always like to start everything off with a slide. And I thought when it talks about decarbonization and what we're talking about today I thought John F. Kennedy had the greatest quote for this, and it was obviously geared towards what happened trying to get us to the moon, right? We do these things not because they are easy, but because they are hard, right? If it was easy, anybody could be test and balance. Anybody could be an engineer. Anybody can be a commissioning agent. And that's not really true. I think it's very important that we serve our roles very well and think outside the box. Again, our learning objectives today, I'm not going to go through this. If you really want to know exactly what this is to, so you can get that one CEU credit. That's why I have to put this slide in there. decarbonization. First, we're going to start out with some of the definitions, right? What is decarbonization? It's basically, it's both the journey and the destination. So you go, what are you talking about? It's reducing and eliminating the embodied and operational carbon. And so let me first explain what's the difference between embodied carbon and operational carbon. Embodied carbon has to do, and there's two portions of it, and I'll go in a little bit more detail in a minute, is talking about from the construction of the building. It's the simplest way to look at it. When you're talking brand new construction, it is the all the carbon that's required from trucks to produce, let's say, the cement, to produce the steel, to produce the ductwork, everything together. That's all considered embodied carbon. Operational carbon, which I'll fully admit, when I first started doing as an EMP, when I first started doing this, that I thought operational carbon was limited to reducing the energy consumption of the building. Well, that's not really true. And operational carbon is both the embodied carbon and the operational carbon that happens from the time the building opens until the time they tear it down. So you think about all the renovations, all the things that happen. They replace the carpet, they replace the ceiling tiles, they paint, all that stuff. So all of that has got carbon. So you get an idea of what it is. And then there's net zero carbon, which is where you are basically you're reducing the CO2 of the building to where it's I'm going to be the first one. I know some of you out there are probably will align with me. How could there be net zero carbon, right? Now I get that. There really is no such thing as net zero carbon, right? Well, the best way, we've all heard about carbon offsets, right? And if you're thinking of like, I don't understand, what are you talking about? What is a carbon offset? Well, the simple Reader's Digest way to explain a carbon offset is, Al's going on a diet, Robert's going to lose my weight for me. That's a carbon offset. That is exactly what a carbon offset is. I didn't lose a drop of weight, but I can tell everybody I lost 40 pounds because Robert did it for me. I did a weight offset. That's what carbon offsets are. Just so you understand, I just want to talk about it in plain, lack of a better term, simple English. Embodied versus operational, I think this is a good graphic, that image that shows you is, if you look at it, if you look at it from here to here, which is all embodied carbon, this is, let's say creating the cement at the plant. This is the cement truck, which is throwing off CO2 to get there. These are all the cranes and all the heavy equipment to build a building. Then operational is everything that happens to the building after it's constructed. All right, I hope that makes perfect sense. So I'm going to go a little bit and explain about what the whole carbon cycle is. There's a thing called upfront carbon, right? So let's first talk about it. Carbon modules A1 through A3, which is the product stage. This is from the cradle to the gate. What that means, the cradle of where they have to mine it or whatever, just to where the truck is going to take it and leave to get it to the site. Think of the steel that has to be milled in the mills, or if they're making it overseas, or wherever they're making the steel, where they're making the concrete and so on. That's what that is. Then the next round of this is modules A4 and A5. Well, these are from the factory to the gate. And then there's the construction installation emissions, like I talked about before, from the cranes, from everything else that does it. Again, this is a high overview for you to understand what the carbon cycle is. If we start to look at user stage carbon, if you start to look at it, all of these have to do after the building. It's in-use emissions. It has to do with the maintenance emissions. What is a maintenance emission? That's from normal, regular maintenance, right? But those could be, most likely, those are all embodied carbon. Repair and replacement emissions. You replace the carpet, right? It's giving up all those emissions. They had to create it again. So you get an idea. I'm not going to lecture you on this. I'm just trying to tell you so you have a clear understanding of where we are. This is the one that I thought was operational carbon. That's what I focused my entire career on, this one little module that, if you're going to think about it, is a small piece in the overall pie, but it's an important piece, and that's where we're going to talk about today. That's where all of us that are on this call make a difference. And then we get to modules 7 and 8. If you wonder about, like, Al, what are you talking about? Operational water use. What the hell has that got to do with it? Real simple, if you think about it, operational water use has to do with, if you think about your water treatment plant that's sending water to your house, they have to expend energy to get it to your house. It doesn't show up by magic. It has to be pumped. It has to. So that's what all that energy is. And then there's the end of life carbon, which is pretty simple. It's the deconstruction emissions. It's to take the building apart and dispose of it. And again, I'm going to remind everybody, Sim did a great job of telling you, but as you have questions, and since you can't just like stop and go, Al, what did you mean by that? I want to remind you to go ahead and type the questions in if you have any. And I'm not saying you do, but if you do, type them as you think of them. And this way we can get to them when the time comes. This is just an overall layout to understand where each of the individual pieces are of that A1 through C4R. All right, 1 metric ton of CO2. All right, so I'm going to give you a little bit of homework here to understand. All right, this is how you can emit 1 metric ton of CO2. It's emitted by using 110 gallons of gasoline. So any of you guys out there that have a Hummer that you are riding around, you know that you only get around the block one time with 110 gallons in one of those things. But that's what that is. 1,100 pounds of coal, 40 barbecue cylinder tanks, 188 therms of natural gas, just to give you an idea. All right, how do you avoid that? There are 40 trash bags of recycled instead of landfill. That means they've gone to a digester and it's converting it to energy, replacing 40 incandescent lamps, which I think is kind of funny. At some point, I'm going to have to change this because there might not, other than Robert and I on this call, there might not be anybody old enough to remember what an incandescent bulb is, right? Because I know a lot of the younger kids have only known what LEDs are, right? They don't know what this is. And then how do you sequester it? How do you avoid it, right? So it's by planting 16 tree seedlings that growing for 10 years, or planting 1.2 acres of forest in 1 year. And so if you're sitting there and you're going, oh crap, Al, we can plant our way out of this problem. Well, I'm just going to give you a little, insight to reality here. If you think about it, I had to write this down because I'm not that smart to remember these numbers. I'm going to give you some perspective. From the EPA, one average natural gas-fired power plant emits 397,959 metric tons per year into the atmosphere, or that is 45.43 metric tons per hour. Or if we want to get really so into it, it's 0.76 metric tons per minute. So basically, in a blink of an eye, all those trees you've planted, we've wasted it in one plant. And just to put this in perspective, that coal-fired plants emit 10 times what I just told you. So I'm just trying to tell you is that, is to understand the reality of life. That's all. I'm not here to preach. I'm just telling you what it is. All right. So being the graphic person that I am, I just thought everybody would like to know what metric ton looked like if you were going to see it as an object. So just think about it. It's a 33-foot tall round sphere. Just to give you some perspective of what a metric ton, if you were going to look at it, because obviously it's a, it's not an object, right? But if it was an object, that's what it would look like. All right, net zero carbon is, again, you understand my whole concept about carbon offsets, but again, we can do what we can to lower the amount of consumption of energy, which is reducing the carbon. It's the only thing that any of us on this call can do, right? But that's what this is. This is how they're trying to do it. They talk about removing the emissions. How can you do that? Well, there's ways to do that. There are things that sequester carbon. I'm working on a project where they're going to create all this energy and then they're going to bottle the carbon. I don't know what they're going to do with it. I'm still trying to understand. We're going to have the same problem we have with nuclear fuel cells. Where are we going to bury all this carbon? But regardless, here or there, it's the reality of in which we live. All right. So now, how do you reduce the embodied carbon? All right. Well, first off, I need you to understand that how do you reduce the embodied carbon? Now, on a brand new building, it's easy. I talked to the architect who, like to build monuments of glass to themselves, right? And I know when I talk to my architectural counterparts, I'm talking blasphemy when I start asking them to reduce the amount of glass in a building, right? They love to put glass in everything. Well, it uses a lot of energy. And as you can tell, that's the cladding here. It emits a lot to produce it, right? And also we tell them don't put the heaviest things on the top of the building, right? Where do they want you to put the chiller plant, the cooling towers, everything on the top of the building, right? Because they don't want to give up room downstairs. They want to put it up on the 40th floor. Well, you have to increase the size of all the columns and everything all the way up and the steel. So that's why you see here that the superstructure is the biggest part of the embodied carbon cycle. I just want everybody to understand that. This is just the way it is. How do you reduce it on an existing? You build nothing or less. What are you talking about? What do you mean build nothing or less? Well, if you think about it, that there's a majority of our construction building stock already exists. Let's not tear it down and do it again. Let's refurbish our existing buildings. Let's make them as energy efficient as we can. That's how you do it. You optimize, in new buildings, you optimize the structural design. You look at an overall whole cycle approach. On new buildings, I've seen them, they've started to go away in some buildings from using steel to going to laminated wood. They looked at, low carbon or carbon positive material. And then they also look at, you reduce the transportation or you reduce the construction. What do you mean by reducing transportation? Try to get something that's closer to the job site instead of getting it from a plant that's 1,500 miles away. You can get something produced that's only 700 miles away or 500 miles away. That's how they're talking about to reduce the emissions. And now we're getting to, this is the meat and potatoes part of this, and why I know that if you're all still awake now, this is the reason you came here, because this is where the rubber meets the road, and how you guys out there play an important role alongside of the engineer, the commissioning agent, and the EMP, especially in the existing building world, on how to make a better building and how we can all work together. So in the first thing I'm going to say here, my very first comment is that, how do you do it? On a new building, you got to work lockstep with the engineer of record, mechanically, be that person, that glue. And in light of working lockstep, I'm now going to introduce you to my brother-in-arms here and my fellow presenter today, Robert. Robert, take it away, my friend.
Oh, thanks, Alec. Too kind. Yeah, like Al had mentioned, when we're in the new construction phase, our test and balance contributions to the project aren't as great as you're going to find them in an existing building world. But if we're able to have the opportunity to work with the engineer early on as part of the design team, then we could communicate having our AABC specifications as part of the project manual, because it's within our specifications that our national standards for total systems balance is defined. And then in preparing a plan review for balanceability, it's essential to where you use the plans, the specifications, and cross-reference with the submittal data. Al has shown that the MEP role is at the use stage carbon or the operational carbon phase, and our roles reside within 10% of that slice, where that slice is only 10% of the overall decarbonization effort. So if the balanceability review, if it's able to provide or identify certain discrepancies within the design, we can communicate this to the engineer, and they may choose to implement it into their design overall, and therefore enhance the design a bit.
So we look at it, and I'm with this following thing, what are the players in this macabre play, right? So you think about it, almost everybody on the call, I'm sure, has been part of a new construction project. And, I always think about it, in the very beginning of the project, I always think of it as, it's like the honeymoon phase, right? Everybody gets along. The general contractor loves the mechanical contractor loves the test and balance guy. He loves the control guy. Everybody gets along. At the end of the project, that nice guy that was the general contractor, now he has become Attila the Hun, right? Because, the project is not on time. Nothing about you guys did. Like, Robert, I'm sure you can tell me how many times that your schedule got compressed at the very end of the project, and they're still pissed off at you that you told them you needed 6 weeks to do this, and they get upset at you when you tell them, I can't do this in 3. You can't you can't name that note in 3 notes, right? It's a reality.
It's not just like that. They ask you, hey, where's your report?
Oh, exactly.
Right now,
but you get the point. I think everybody understands that at the end of the project, there's the test and balance guy, the tab guy, the commissioning agent. Everybody is the villain at the end of this particular play here. So I just came up and to just show the roles here. So I kind of saw it as that in this here, as far as we're concerned, the engineer creates the design vision, what he had in mind. The commissioning agent is just there to help to make sure that vision gets implemented. So that's why I wanted to show it in the order that they are. And then there's the mechanical contractor, and then the control guys and you guys all work, under him, right? That's the way our traditional design, bid, build world works. We can say different, but that's not the way it is. That's exactly the way it is.
Right, and I was referencing performing that balanceability review, and this is an example that just happened recently where I was performing this review, and you check out the air handler equipment schedule, and the column for the chilled water coils, the GPMs tallied up to, we'll say, 1600 GPM, and it's a variable primary system, and there were 3 chilled water pumps in parallel, 600 GPM each. So I'm approximating 30 to 40% diversity in the system, which is quite a bit, but that's only where it began. It didn't end there. When I got to cross-referencing to the submittal data, I saw that the control submittal, their package and selection of the pressure independent control valves, they tallied up to the same GPM, but the order was put in for the control valve bodies to be 3-way type configuration. Well, that's not going to work in a variable primary system. So I got looking further into the drawings, and in the detail sheet where we had the detail of the chilled water coil, you could see the piping configuration there was identified with the 3-way control valve. And it didn't say anything else about a 2-way or only having them in these certain locations. So, our standards make provision for this, the tab review, but also the observation, early in the construction, that's where you're going to really find the installation process, installation configurations, which may be detrimental to the efficient overall operation of the equipment. Yeah.
So here, here's the existing building. Now we're going to roll over. This is where I think all of us here today make the most impact, right? Because you got to think about it. When we go back to this model right here, the engineer of record has already he's set the design, he's worked it out with the owner. It doesn't matter if we agree, disagree, it doesn't matter. That is the design, that's what's been bought and paid for, right? We have no impact other than make that work as efficiently as we can in all our trades, whether it's commissioning, whether it's the tab guys, whether it's the contractor. That's all we can do. But when we get to the existing building role here, we can have a major impact, right? Remember I said a few minutes ago, build nothing or less. Well, that's what I meant. You take an existing building and you can make it run like a champ. You can replace the HVAC, be more efficient. Again, and Robert and I have some stories to talk about later about how we can show how you did that. And, I'm sure him and I could talk all afternoon on different things that we've done, but we have two specific ones to talk about. I go, and you got to think about it. At this point, the majority of the operational impact is made by improving the system performance, right? And making, putting in smaller systems so there's less impact. Is so you understand that, right? And then the players in this particular torture chamber, because that's how I look at it, all these things, I'm not trying to make it that we will never get along, but everybody's forced together. Every one of these things becomes a forced relationship, right? Because you may have never worked together. But while we are put together, each person has a very distinct level playing field role here. And that's the major difference. And I'm going to show you that here, is that while I'm an EMP, so I may go ahead and I may come up with the concepts, and then the CXA is going to oversee it. Well, in this particular case, I would have two roles because I am the EMP and I could be the CXA. Well, I would never do that, only because I believe in the independent third party of it. So even if we were the design firm, I would have somebody that had nothing to do with the project do the commissioning on this, so they have that independent eye. But then you see where I put the engineer, because a lot of times, unless it's a control project only, if there's better, you'll need an engineer of record to be part of the project, but he is on level with mechanical contractor. Nobody has there's no hierarchy once we get here. There is no hierarchy. Everybody's on the same plane. And actually, if I was honest about it, to think about it, the tab, if I had to redo this again right now, tab might have been over here, because tab is as important as an initial part of this role. Robert, I've been talking too much. What do you think?
Well, listen, Al, if I was fortunate enough to become a part of your team, I would certainly it would be a smart decision by you to select me first off, but I'd be a key and integral role in the retro commissioning process. We would go into a facility and provide a complete investigation, taking measurements across all the equipment to establish a baseline, so to speak, to where we could strategize together to determine what corrective measures could be put into place, and then rehabilitation, and realize the improvements made to the system. So with our experience, from what we've seen, most everything out in the field, and then also in existing buildings, we're going to find these conditions and be able to highlight them very early on in the investigative process. Okay, so I think you touched on it, Al. Given you the EMP, you be serving as EMP on a project, you've got a role direct with the owner in selecting your team. So I think a good test and balance professional is an asset. And if anybody's fortunate enough to work with you, then they'll be having a lot of work throughout the year, I'm sure.
Yeah, and it's very true in what you say though. Is like, and I be here in Tampa. I won't say who it is. He is at definitely AABC, but the point is, every time that I do it, I only hire one guy to be part of my team because I can trust them. And that's an important thing that you guys out there, if you work shoulder to shoulder with your EMPs and CXAs, so sometimes they're one and the same, and they're also design engineers. So like I have 3 hats in this particular party. If it was me, I only go to one person. This could be more work for you guys going forward. And just a real quick story, the way Robert was talking about having somebody come in and test everything. Well, I had a project here in Tampa where we got started. So I had the test and balance guys do an initial test and record of where all the equipment was, right? I needed them to do that. Well, I found I don't remember exactly, I want to say there was 8 different air handlers, but 4 of the air handlers, based on the actual, I had the cut sheets and schedules from the original design. Those air handlers were supposed to produce 40,000 CFM. 4 of the 8 was supposed to do 40,000 CFM. When we tested them, they never got beyond, I want to say it was between 26 and 28,000 CFM. Well, the first thing I did is I went to the owner and go, hey, here's what we found. This does not meet the design. Have you had any cooling problems that you've yet to tell me about? And are you expecting these air handlers when we walk away to be doing 40,000 CFM? And he looked at, and the owner looked at me, who's also an engineer, that's the operator of the building. He looked at me and goes, why would I want to do that? I go, I don't know, but I don't want you coming back later and going, hey, you're supposed to do 40, they're only doing 28. What's the matter with you? So I'm just telling you, that's why it's very important in the very beginning to do that.
All right, Al. Well, thanks for acknowledging us TAL professionals in the role in the retro commissioning team. So looking at this slide, I can't help but perform an assessment of it as well. It's a funny slide, and who doesn't love minions? In this case, how many minions does it take to remove a light bulb? Just looking at them, their technique is chaotic at best, very, very clumsy, and the revolving efforts is ineffective. But ultimately, the goal is to reach an efficiency here by the changing of that light bulb, okay? And ultimately reducing our carbon footprint. So Al, looking at this, I'd like to ask you a question. It's regarding the smart minion there, the one that's not wasting energy by carrying the heavy load. But what is it that he is carrying? What's in his can there?
Yeah, it's kind of funny, is that, while he's the smart minion and he's not wasting any energy, he's about to replace an incandescent light bulb with an incandescent light bulb, and he's not going to save 1 ounce of energy, right? So it's kind of funny. He should be doing LED. I mean, obviously, this was not set up for us to be using as a metric for how the minions are going to do something, but it's a true thing. It's a good observation, because I remember, truth be told, when I saw this as, well, this is teamwork. They're working together, right? That's how I saw it, and that's what I think we're all supposed to do. And I was looking for that funny thing about teamwork, and it was kind of weird when you pointed out that they're replacing an energy inefficient light bulb with an energy inefficient light bulb. So I just thought that was kind of funny.
It is.
So, going from this point forward, how to test and find wasted energy issues. Here are some common, obvious ones, and maybe just not so common. So, Robert.
Yeah. So in finding the wasted energy, these 5 chiller conditions, you would get involved by using your instrumentation out there and collecting the data, for real-time data for analysis. So the best scenario is for the test and balance professional to work alongside of the CXA and the controls contractor. The field data that's recorded is the driving force in the development of the corrective measures necessary to bring the chiller back into proper operation. So we would take the actual load across the chiller, DPs across flow meters, verify
Oh, well,
offsets which
Robert,
may be necessary in our diagnostic testing.
all
Yeah.
right. Yep.
Thought you had a question.
Oh, yeah, no, you froze up, my brother. You froze up, so
Oh.
I was about to start filling in the dead air.
I did see my internet connection. Okay. Well, I hope I'm coming through okay now.
No,
So,
you're fine up until that one little point.
which the point was just, the collection of the data, the actual data for use in the diagnostic testing, and ultimately the development of the corrective measures.
All right.
Okay.
I think everybody needs to understand what Robert's put here is from his world experience of what he's seen, that these are not, all the things. These are just some of the highlights of the most common ones that, he's seen, and I've seen them too.
Right, like in chilled water pumping here, right? Low flow, high TDH is common. You see that quite a bit. But what's going to lead to this condition? If you're going to start there at the pump, you got your triple duty valve. I've seen where the check valve portion of the triple duty valve has stuck, whether it be fully closed or partially open, but it has stuck, and the contractor there gets his hammer and beats the heck out of it, or we just change it out. You may find on the existing building where you came to that same valve and somebody's trimmed it back for whatever reason.
Yep.
It could be just as easy as a dirty system where your suction diffuser may be impacted. The VFD may not be getting the proper signals to sequence and ramp it up, or it's in hand and somebody put it at a low speed. So, it operates off a differential pressure out there in the system. I've seen many times where the high-low ports are impacted, again, probably through chemical treatment or the lack thereof, or the peacocks are closed up and isolated if there was a leak or something. I think you got the pump cavitation there. I'd initially go and take a look at the makeup water assemblies, see if the isolation valve has been closed, or if the pressure reducing valve has been adjusted lower, or if it was replaced and it was replaced with an insufficient range. Well, those are contributing factors that would lead to a low and net positive suction head requirement. Cooling
Or
towers.
one other thing,
Yeah.
just on that one, just to what I've seen also, and guys, if the engineer didn't know what he was doing, and I will say that with all due respect, that they didn't, because I've met more mechanical engineers that don't know crap about hydronics, and they oversize the pumps. If your pump is so oversized, it will roll out all the way on its curve, and you're producing so much flow, it will cavitate because it's below the curve of the pump. And the way you would know that is if your pump is sitting there and it's rocking along with the cavitation. It's, guys, everybody here knows, they understand it on a fan curve, that you don't operate a fan to the left of the curve, right, in the unstable range. While below the curve on a pump is the same thing. So I just wanted to point that out to everybody.
Which is why we have the triple duty valve. We adjust that and put back pressure back onto that pump. But then how often, well, as a tab professional, we would bring it back to the tab position, mark the valve, because some contractors, controllers, or owners want to be able to have the full capacity of the VFD. So we'd mark the balance position and then open it back up and allow the variable frequency drive to control to the DP out there in the system.
Right. So now the one thing where the only time I think you and I are ever going to disagree, I hate triple duty valves. I absolutely hate them with a passion. I'd rather and when I've had an owner tell me they want to put them in, I make them put a valve above the triple duty valve. Or otherwise, there's no way to replace it without draining the system.
Yep.
I'd rather just put in a balancing valve. That's just me. That's just from my experience.
But
and
then
the same thing
I'm also on a project right now where we've got the pumps in parallel, and without that check valve in place, the two idle pumps are rotating in reverse. That's indicating that we got backflow through them. Not a lot, but it is happening.
Yep. So we're talking about now, we're going to go to the air side. We've been talking about the water side. Let's go to the air side.
Mhm. Okay, right. Looking at the supply fan undersized or overperforming in an existing building, well, there may be a chance. I think you might have touched on it in your example, but maybe not. Let's see. I've been to projects where the connected load to the system has had an impact on its capacity, making it either oversized or undersized.
Right.
And that's one of the roles that we play in the RCX team, is to identify these areas where there's been changes made, so that now we could take that back to the air handler and make the adjusted fan speeds there. Service-wise, performance-wise on existing equipment, a common item would be the return outside air damper. The linkage may have slipped or broken. If it broke and the outside air dampers closed or lowered, you're going to have an issue with the occupant wellness, not having the required ventilation and air changes. And then the same thing, if it's the opposite way where it failed open, now you've got an issue potentially with the building pressure, where your exterior doors are standing ajar because you can't relieve the outside air intake. That would be also fall into the wasted energy, because now you got to cool heat all that additional air, outside air intake. Or how about where you find the filters that are not being maintained, or they're being maintained, but they're completely filthy, dirty. Your fan speed has to overcome that, so you start increasing your fan RPM. Or if the filters are completely failed and just fallen right into the face of the hot water coil.
Right.
For the Vegas market anyways, the heating coil is there first upstream. I mean, all of that leads to wasted energy. Duct leakage, sensor failures, all of it contribute to the operation of that air handler. Oh, terminal units. These issues, any issues that you found within the terminal unit have a direct impact to the occupants' comfort, discomfort, and wellness. Types of examples that I see out there nearly 100% of the time are associated with the calibration of the controller, the operation of the damper, the reheat coil face may be impacted with insulation. That happens quite a bit on systems where you have some internal duct lining.
Well, one thing you hit on one thing here that's a personal pet peeve of mine is on improper airflow and calibration. The reason I say it's a pet peeve is because our control brothers all, from I don't care the manufacturer, it doesn't matter. They all say the same thing, that their boxes are auto calibrating. And I tell them, why are you lying to the owner? Because they believe you more than they believe me, because you're the guy that knows. And they go, but I'm not lying. I go, yeah, you are, because and when I tell an owner, auto calibration means that the box, when it wakes up in the morning, it goes to 100% open and says, hi, I'm 100% open. And then it goes to 100% closed. And it acknowledges the same thing. Doesn't say how much airflow it is.
That's just by a signal to the actuator. That's not actual proof.
And it
ends up with a number on the screen. You don't know if it's true or not.
Correct. I agree. So, but anyway, yeah, as you can see, there's a ton of things here that we can go over, and just in the inference of time here a little bit, you can look at these, we look at controls, Robert, as well as I do. All these things are on every single one of the things we just talked about. Wouldn't you agree?
Yeah, working with controls, that'd be just an operation of verification, your point to point.
Exactly.
Programming, like you said here. But you've got a slide here coming up, right? There you go.
Yep, here it is.
This is where you've got a case study of in excess of 8 years of trend data, right?
Right. Yeah, this here was an airport where it turned out to be a cup replacement, or a central utility plant replacement. but we were able, they had literally, I think it was over 8 years, but 8 years was the number that's in my mind, of where every winter the lowest tonnage throughout the whole year, which included, and it gets a little, while it may not get as cold here as it does, let's say, up in the Midwest or anything like that, but we do get into the 40s and 30s sometimes here in Tampa. Well, it got down, the smallest amount of tonnage we ever saw in any of that 8 years of trending was 800 tons. That plant was a primary, secondary plant, right? Constant volume primary, variable flow secondary. Well, when we converted the plant and we went to variable flow primary, again, it was a brand new plant, but that's not what, it didn't make the building any more efficient, right? It only made the plant efficient. Well, what we saw here is that in the middle of the winter, we couldn't keep the plant online because we had 1,400 ton machines. We couldn't keep it because we were lower than 140 tons. So I'm just saying that a decarbonization thing, it could also be by retrofitting an existing plant from primary, secondary to variable flow primary, if the chillers can do it. But again, this is just to show you that a change of system scheme can make things work better. Robert, why don't you tell us about yours?
Yeah, so this slide here, we had the chilled water system that was just operating inefficient at best. Here's an example of all the items that were, contributed to its operation. And then it was through working through these and bringing the system back into a balanced condition that for the sake of time, let's just roll over to the next slide, because that's where all the numbers are.
Sure.
So, presuming that we did correct each of the issues that we had identified on that previous slide, and brought the balance into play, the corrective measures improved the chiller's efficiency, say, by 5%, okay, as it is in the example here. And that's a very, very achievable number. If you remember the review that I did earlier with those three-way valves, that's a lot of it's different projects, but that's something you would pick up in the design phase if that's where you were working at on a new project. So given these following factors here, this 800-ton chiller, it did have a nameplate of 408.2 kW total power rating, and that's 1.39 using our formulation of BTU per hour. So when we take the kilowatt hours, right, I think I know by search, the average cost for electricity is 16 cents a kilowatt, right? So at 16 cents a kilowatt, with that 5% improvement, that's $3.27 an hour. And that's over the life. The example says 2,000 hours a year. So that totaled through calculation over $6,500. That energy savings, that 5%, also calculates to over about 41,000 kilowatt hours. And then the formula to calculate that to metric tons, you multiply it by 0.4 kilogram per kilowatt hour. That gives you the metric tons. In this case, it's 16,328. Dividing that by 1,000 gets you the 16.33 metric tons of CO2. So that's the realized reduction in the carbon footprint just for that year. And if you, remember where you put the 1 ton example of that 33-foot bubble. Yeah, so calculating it out to the 16.33 tons, that's a 539 for a visual, 539-foot diameter bubble.
Right.
It's over, it's over 22 cubic feet. Yeah, so that's a lot of CO2.
Yep. And I think visual makes it easier for somebody when you just talk about it, and when you don't, it's easy to say a number until you see it visually.
Mm-hmm. So in summary, I'd like to close by saying that we, all of us as EMP, CXA, or a TAB professional, we all provide a key role, not just in the retro commissioning process, but in all projects, large or small. And we should recognize this as a fact and be proud of that, our contribution to every project. If we perform our job correctly, the outcome of the facility's operations is the best for occupancy, wellness, and sustainability, which is all that we try to bring to the table as professionals. Thank you.
Yeah, I agree with Robert. I think that us working shoulder to shoulder together to make this be a better together, I think we work better. That's the way I see it. I always, I've always been that oddball engineer of where I always thought that, working lockstep seriously with the tradesmen and stuff to understand, because while I might be an engineer, I'm not the guy that turns the wrenches, right? I'm not the guy that, I've done a little bit of that in my life. I'm not that guy. Like, I can't do what Robert does, right? I'm not the guy. Yes, I've done flow measurement. I have an Alnor, and I can go out and I can do some stuff. Does that make me a test and balance guy? Absolutely not. So we all have our individual strengths and weaknesses, and if we work together, they're all strengths as a team. That's how I see it. And that's how, so when I'm talking to an owner, that's how I see it. So now we get to the questions. Does anybody have any questions out there? Sim, is there anything that anybody have some questions for us?
Yes, Alan, Robert, we do see questions in. To start with this question from Rishi Raj, he says, what could lead to the low delta T problem in chillers? Doesn't it just depend on set points?
To answer that question. No. Oh, yeah, you go.
Yeah, no. What could lead to the low delta T problem in chillers? I would have to say load, building load or flow. That's when you're coming in at 40, 46 and you're leaving at 44, right? Because there's no load, there's no heat transfer out there in the system. And what was the second part of that question there? It was a set point? No,
yes, it says, doesn't it just depend on set points?
No, I don't believe it would be necessarily just a set point. This would, I think, align more with a variable chiller. So that would be its ability to turn down and have a turn down ratio. So you could take a chiller running at the 800 tons and turn it down to 200 tons. So you can keep the split manageable to where it's not short cycling as often.
Well, to go a little bit further on that, when you talk about primary, secondary, if you have a constant volume on your primary side is on the chiller side, depending on if you overpump either way, either you are sending warmer water out or you're sending colder water back, because they never equal each other. So regardless of the set point, that's, anytime that the production side, which is the secondary side, the chiller side, versus the distribution side, anytime they're not perfectly aligned, you are creating low delta T, a differential in temperature either way, right? And then so it's not always, and then where Robert is correct, but at some point you get to a minimum on a machine. Let's say an 800 ton machine. Let's say it's Carrier or Train or whoever, and the minimum they can go is 1 GPM a ton. Well, that means that regardless of what the tonnage is, let's say they only need 200 tons, they got to run 400 tons worth of water through the system. So sometimes you can't avoid it. And that's why you'll see designers come up and put pony chillers in for those smaller offloads. Sorry, I might have gotten off on a tangent, but next question.
You're correct. Every chiller has a minimum flow that must be established, and that the test and balance would definitely work with the control contractor to ensure that either if there's a bypass or just a flow metering device, that they are calibrated so that you're not dropping below that minimum flow.
Got it. Thank you so much. For the next question, I see that's a question from Jonathan, and he says, for a variable flow pumping system, do you think a 3-way control valve is necessary at the most remote coil?
Not if the furthest remote coil is a very small coil. No, I think what you would do is you would strategically select where you would locate the three-way valve. Most often you'll see it written in the documents that it's speed 2/3 of the way down the system. What I don't like seeing is engineers that say we're going to control the plant pressure, because ultimately, in my opinion, the plant pressure is just like the TDH on your pump there. You basically don't have any pressure drops out there when you're entering it. Supply and return pipes go straight from and back to the pump. So 2/3 of the way down, you see that written a lot, and then strategically located to where maybe the design is the three ways out there in the system equates to the minimum GPM required by the chiller. So again, that would be a strategic location, not just the furthest out.
Well, this is one of the few times today, my brother, you and I are going to disagree.
Uh-oh.
I don't, no, I don't put any three-way valves out in the system. I put a bypass at the plant. I put the DP out into 3/4 of the way out in the system. If there's multiple ones, I may put multiple sensors out in the system and average them, or based on the worst one. Because I think if I got a bypass at the plant, why do I want to bypass it out in the system? I'm just causing myself. That's been my experience, and those systems work fine for me. It may not work for everybody, but they work for me. Again, this is why we can talk about this, because we all have different experiences. Sam, what you got?
But if it's a long run and you've got a little bit of flow out there, your temperature transfer will happen quickly.
Again, I agree. You have to look at every condition is a little different, and I agree with you.
But that's a good question. That did bring up some good debate there.
Yep.
Thank you.
Perfect. I do see that Peter is here with us, and he's dropped a comment and he says, low chiller load can also be due to balancing. A project I was involved with, every balancing valve on the fan coil unit was open 100%. Delta T was 1.8 degrees, and 3 primary pumps were running at 60 hertz each. So that was something I wanted to share.
I've seen that too. That's a control problem. That where I've seen, and I'll be the first one to say that's when I've had a bad test and balance guy, because they went out and they set the DP out in the system very high. And if you had a primary, secondary, variable flow primary, it looks at the delta T and it modulates the pump. When you did primary, secondary, the secondary pumps look at the DP out in the system. And if the DP is not satisfied, it starts the next pump. Continues to not be satisfied, it starts the next pump. So you can see a condition where you have 3 pumps running when you only need 1. And because the DP is set so high out in the system, and the valves are not, controlling properly, because now you're sending warmer water out. It's crazy stuff that goes on. That's been my experience of what I think has happened. That's what I've had happen.
What if the filters on the fan coils were plugged?
Oh,
What if the airflow on the fan coil was low? You're going to have a small delta T at the coil, which ultimately results in a low delta T back at the chiller.
I would
probably need a little more information on this one.
Yeah, the way I gathered from Peter's question was that it was a blanket. They were all like that. So yes, you could be right. All of them had dirty coils, dirty filters. That could be also. But if this was a relatively new job or whatever, and you're just going out there, that could be also the case. Again, you're right. More information is needed to answer that question.
1.8 degrees is that's a tenth, right? Rule of thumb, you'd figure you got a 18-degree delta T on a coil. So is this an oversized control valve? Is it low airflow? I'd have to look at a couple different things to give you a precise answer on this question.
Oh yeah. But if you're getting a 1 degree, you're over pumping the coils. Is what's happening.
Nope.
So
or no airflow. One of the two. You're right.
Yep.
You're not getting the heat exchange.
I agree.
Okay, thank you. Good question.
Next.
Perfect. Just a quick reminder, it's already 3, but if you are okay, we can go ahead and take one more question.
Sure. Go ahead.
All right, perfect. So this question is from Keshav, and he says, how do you communicate the value of TAB work to building owners focus solely on ROI, especially in the context of decarbonization goals?
Let me weigh in a little bit because I just had that slide where we showed you just a 5% improvement on the efficiency of a chiller with those existing issues resulted in that $6,500 a year. So if you got 65,000, that's a 10-year ROI just on the test and balance. That did not include all. How about in the case of the design review where we saw the three-way valves? Can you imagine running an 800-ton chiller full bore throughout its life without finding that issue? So by finding that issue, we're able to save pump operation to the chiller, to the cooling tower heat rejection. And you run the math now on multiple components, that $6,500 is going to go up quite a bit. Would you say so, Al? From an EMP standpoint, it's just all about kilowatts. And if you can give an owner a dollar amount and he knows what he paid for your services, the commissioning authority services and test and balance lump sum, I think most times I see an ROI less than 5 years and sometimes a lot of times 3.
Well, the thing you went where I was going with this, I think the tab guy by himself can't sell that soap by himself. Not because you guys can't do the work, that's got nothing to do with it. But you're gonna need if you go and you teamed up with a EMP, they're gonna show that, hey, by doing this stuff, we're gonna save this much money. You're still gonna get the work, and it has to be, let's think about it. Every time I do a retro commission project, I start out and I tell the owner, budget for 25% of your VAV boxes have to be recalibrated. We're going to test them and we're going to recalibrate them. I said, but I'm telling you right now, put a little pot of money on the side and you're going to have to recalibrate the other 75% of them, because my experience from doing this long enough, 100% of the time, 100% of the boxes are out of calibration 3 to 5 years out. And that alone saves money. So hope that answered your question, my friend.
Perfect. Thank you, Alan Robert. And I think with that, we're going to go ahead and wrap up the Q&A session. Can we move on to the next slide, please?
Oh yeah, right. Let's go to the next slide. There we go.
Perfect.
Sorry.
Thank you so much, Al. No, that's okay. Well, thank you so much for joining us today. We hope you found the session insightful and full of takeaways that you can take and bring back to your projects. Also, thank you so much, Alan Robert, for such an excellent presentation and discussion. And thanks again to our sponsors, Ganamax. Before you leave, a quick reminder that we cannot wait to celebrate the 60th year of TAB Excellence with you at the 2025 AABC annual meeting in beautiful Omni Amelia Island, Florida. Join us from October 22nd to 24th for ocean views, networking, and expert insights with the top professionals in test and balance. You can go ahead and learn more about this by visiting our website, www.aabc.com. Thank you so much again, Alan, Robert, and everyone for joining us.
Yes.
Everybody have a great afternoon.